recursive complexity T of n is equal to 8t of n over 2 plus n squared. All right, so the question is this complexity something we can solve with Maxwell's theorem? Okay, and we know it. Why? Because we see that there's only a single recurrence. Okay, and we know that there are 8 branches, and then we have an actual complexity. Okay, so we can try to solve it. Let's see how it would come out. So we would have f of n is equal to what? N squared. Good. And then our n to the log b of a, which is corresponds to what? What does that correspond to? Height.
The
Number of leaf nodes. Would either be work. So that would be n to the log 2 of 8, which would be what? Thank you. So looking at this, these two results here, is the complexity of the recurrence growing exponentially, decreasing exponentially, staying the same level to level? It is growing, because we can see that the complexity ends up at n cubed and starts off at n squared. Therefore, we can solve this immediately and say that this is going to be what? So we can say T of n is an element of theta of n cubed. Okay? Does that make sense? Okay, so let's take a look at another example. Let's say we have T of n is equal to, let's say, 4t of n over 2 plus 2t of n over 4 plus n. Now, is this something that we can solve by Maxwell's theorem? No. Okay, what's the problem? Well, the problem is that there are two recurrences and they're different. So this is n over 4, this is n over 2. If this was 2t of n over 2, you could simply say this is going to be 6t of n over 2. But, so this is not solvable directly. Let's make this a little bit simpler. I'm going to try to make it like this. So, let's say this is our complexity. It's still not solvable by Maxwell's theorem. So, let's say we wanted to use the Maxwell's theorem anyway. Okay? How could we use the Maxwell's theorem? For example, we want to find out, is this really theta of something? But we can't use the Maxwell's theorem. So we can try to adjust this. So basically what we're going to do is we're going to rewrite this. So this is obviously, this is the complexity. We can say, let's look at T1 of n. So this is a different complexity. And I'm going to rewrite it like this, is equal to 4t of n over 2 plus n. Are these the same? Are these the same? They're not the same. But what can you say about T1 versus T? How do you relate this T1 to T? It's going to be, I would say, it's a good answer. So T1 will be greater than or equal to T. It will be no less. It will be at or higher. Because T of n over 4 is going to have lower complexity than this part. If you just had this or this, we know that this is going to have a lower complexity. So therefore, if I take this and I say, okay, let's increase its complexity so that it matches this, so this becomes an upper bound. Okay, so why do we do this? Because the upper bound is now applicable for master theorem. So if we just look at this one, we'll have f of n is equal to n, and we'll have n to the log b of a is going to be n log 2 of n to the log 2 of 4, which is 2. So therefore, we would say that T1 is an element of theta of, okay? So that means we can say T of n is an element of big O of n squared. Can we say little o? Nope. Can't say little o because little o means that it's strictly lesser, and we don't know. Upper bound doesn't mean it's a higher complexity, it just means it's an upper bound. Could be the same theta complexity, but just a higher instruction count, for example. Okay, so now what we can try to do is something else. Anything else you can think of doing? We can try to go on the other flip side of it, which is what? Let's look at the lower end. So rather than looking at doubling up, increasing this one to match that, we can look at 2 of n is equal to 4t of n over 4 plus n. So now we have created a lower bound using master theorem. Let's see what it gives us. It's applicable, so therefore this is going to be equal to T2 f of n is equal to n and n to the log b of a is n to the log 4 of 4, which is n to the 1. Therefore, what do we have? What we have here is we have T2 is an element of theta of what? No. N log n. Yes. It's an element of theta of n log n. So that's very, very interesting. Right? So it shows us that the lower bound is n log n, and the upper bound is n squared. We still don't quite know where this one is. But we know it's no worse than this. We know it's no better than this. Now, in reality, it's possible that it's this one, or maybe something in the middle. So, how can we try to get a better idea? Well, this certainly is very helpful, right? So now we can also say, based upon this, is that T of n, original one, is what? An element of big omega, right? Of n log n. See how we can use these things? Can't use little omega, because we don't know exactly what the proportionality is. So, let's take a look at this function again. Now we can look at this function and try to see what happens if we build a recurrence tree for this function. So if we build a recurrence tree for this function, we assume that the input into level 0 is n. So therefore, the actual cost at level 0 is n. Right here. And then there will be 2 branches here and 2 branches here. So this is the recurrence for T of n. So we're going to get this one branch here. This is going to be n over 2, right? And when n over 2 comes in, into this one, n over 2 comes in, there'll be recurrences, but the actual cost will happen to be n over 2.
Yeah.
If this was n squared, the actual cost will be n squared over 4. You understand what I'm saying? I don't want to go too fast, but I want to make sure that you're following me. Okay, so it just happens that whatever we're passing into recurrently is the actual work, because the work, the relationship between what goes in and the work is one-to-one, linear. If this was an n squared, then the work here would be n squared, and then we'd have to take n over 2 squared, n over 2 squared, n over 4 squared, n over 4 squared. This is easy because it's just a linear relationship. So ends up being the 2 n over 2's and 2 n over 4's. That's the recurrence. So the recurrence tree is showing the actual work. We can expand it, right? All right, so now each of these is going to generate 4 branches. So let's see how far we can go without getting dizzy. So n over 2 comes in, and then we're going to take 2 branches of half of that. What's half of n over 2? Is n over 4. So we're going to have n over 4. We're going to have n over 4, but then we're going to have n over 8. And n over 8. This will be the same. N over 4, n over 4, 8, 8. Now, these guys, n over 4 will come in, and then we'll have 2 branches at half of that. So it's going to be 2 branches of n over 8, n over 8, n over 16, n over 16. And now the last one will be the same as this one. So we're going to have n over 8, n over 8, n over 16, and n over 16. Okay, and of course it continues. Now, one of the things we do know is that this tree, if you follow down all the way down to the left branches, versus following all the way down to the right branches, this tree is actually longer on one side than the other side. Which side is the longer side? Which one? The right one. The right one is the shortest. Because the rightmost branch is always n over 4, n over 16, n over 64, n over 56. So it's going to go to unity the fastest. So this tree will eventually end up at unity here, but here it's still going to have a ways to go. So it's growing, it's decreasing its size exponentially with a base of 4, but here it's only with a base of 2. So the tree will kind of have this kind of a shape where basically it'll be here, but longer here, and then it'll be kind of jagged up to this point to get to here. Because it's the combinations of 2's and 4's. Well, this is all 4's and all 2's. You get the idea, right? Okay, but let's see if we can see some kind of pattern. So what we're going to do is we're going to try to assess the amount of work being done in each level. Well, it's very, very easy to see that level 0 is just doing work equal to n, because there's only one node, and that's the level 0 node. Right? Here, we have n over 2, n over 2, it's n, and this is another n over 2. So what we really have is what? 3 n over 2? 3 n over 2. So is it increasing or decreasing? Looks like it's increasing. Okay, so now let's see what we have for the next level. We gotta be really good at adding fractions, so we don't make any mistakes. So here we have n over 4, n over 4, n over 4, n over 4. That creates n. Now, n over 8, 2, 3, 4, 5, 6, 7, 8. That's another n, right? And then we have 16. So we have 16, 16, 16, 16. How many 16s? 4 16s. Plus 4 16s is 1/4, right? Let's keep 16. So we'll say 4 16s n. So sometimes we can see a pattern develop here. Let's try to add all these together to find out what the total amount of work being done at level 2. So if this is going to go into 16ths, then this becomes 32 16ths. 32, 33, 34, 35, 36. So this would be 36 16ths n, right? Okay, so now to see if there's a pattern, we might want to go back here and do what? And put this also into 16ths to see if there's a pattern. So we have 1.5 n, so in terms of 16ths, that would be what? What we have? We have 3 over 2 n, right? So that would be 24 over 16. 24 over 16. 24 over 16 n. Do we see any kind of pattern here? I hate to go another level. I hate to go another level to see if unless we can see something here. This first one obviously is 16 over 16, right? So 16 to 24 doesn't seem like a really nice transition. 1.5. Oh, there you go. Okay. So now, yeah. Okay. So 3 over 2 is the pattern. So basically, so let's rewrite this. That's good. Good job seeing that. Yeah, I was like a split second behind you. Like, yeah. So what we have is we have 3. So again, this was 1n. This is 3, 1.5, and then 3 half squared is going to be what? 9/4.
Yeah, that's right.
9/4, and 9/4, of course, is equal to 36 over 16. So it looks like we can write this as, well, this is going to be 3 half n, and this will be 3 half squared n, and this will be 3 halves to the 0 power n. And of course, I'm really happy to see the pattern. It's a nice thing, and everybody's happy to see the pattern. So we can see how this is going. So the question is, what happens when you do all this? Well, basically, if you do all this, then you can see that the summation over all levels, and this is hard to say, because summation over all levels, we don't know how many levels there are. In fact, we can determine that there are fewer levels here, there are more levels here, so therefore the levels are not all the same. Some of them drop out, but we'll assume they don't. We'll assume they go forever. Can we do that? We'll just say they go on forever. They never end. Of course they do, but we're going to assume they never do. So what we're going to do is going to do summation as I goes from 0 to some number, and we're going to say it's going to be 3 over 2 to the I, and we're going to multiply that by n. And so we can go to some arbitrary value. Of course, so let's use this value, upper value, we'll just call it h. It doesn't have to have the same meaning of height, but some value. And so therefore, we can rewrite this because n is not a function of I. We can say this is equal to n times the sum as I goes from 0 to h of 3 over 2. So we have a small problem. We have a small problem. Because when we assume that the levels just keep going and going and going, which of course they don't, but sometimes we can assume that they do. If we can find that the ratio from level 1 to level 0 and from level 2 back to level 1, if that ratio, which is 3 over 2, if that ratio is less than 1, then what happens is the summation here, even if we go to infinity, converges because it's an open sequence. if this number 3 over 2 was 2 over 3, this whole thing would converge even if this went to infinity. What kind of sequence would we have? We don't have it, but if we had it. And in the slides that Luke has showed you, I think their recursion tree ended up having 5/16 was the ratio. Remember that? So it was like n, or n squared, 5/16, n squared, 5/16 squared, n squared, 5/16 cubed, n squared. Remember that? In the slide? Sort of, maybe? Did he show you that one? No?
I think so.
Oh, I'll show you. Okay, so the idea here is we cannot find an upper bound here in t here. But in other cases, we may be able to find it. We can try a different function as well. So for example, let's see what would happen if we did this one. So now we change the function. Let's keep this one the same and I'll write another function. This is never going to be fixed, right? So let's say we have another function, say t of n is equal to t of n over 2. Let's say plus t of n over 4. Keep it simple, really simple. See if we can find a pattern. Plus, and let's say n squared. Is it possible that this function complexity is less than n squared? Is it possible that the complexity is less than n squared? No, because level 0 is already executing n squared, so that's minimum. Okay, so now, but we cannot solve this using Master's theorem. So we can say on the recurrence tree we have n squared is the amount of work being done at the top level. And then here we have 2 branches. The first branch is going to have n over 2 squared, which is going to be 1/4 n squared. Right? And the second branch is going to take n over 4, which is going to be n squared times 1/16. Okay? And here, so this is n. This is n over 2. Now the left branch is going to be n over 4 squared. So this is going to be 1/16 n squared. And this is going to be so this is going to be, so this is basically, this is n, right?
Yeah.
But the function is n squared. This is n over 2 all over here. And this is n over 4. Not n over 4, no. Well, if we're going this way, it's n over 4. But here, it's n over 2, and then we're dividing it by, so it's going to be n over, this is n over 2. We're going to the right branch. So n over 2 divided by 4, n over 8. And we're going to square it for the actual work. So what's that going to be? 1/64 n squared. This is the right branch, so this is already n over 4, right? N over 4. And now we're going to go, so it's going to be the same as this one. So this is going to be 1/64 n squared. And this one right here, n over 4, n over 4, n over 16. So it's going to be 1 over 256 n squared. So what we have is our total work. Again, this is going to be an uneven tree. It's going to be short on the right side, longest on the left side, and in between it's going to be uneven. So here we have n squared. Here we have 1/4 and 1/16. We add them together. So it's 5/16, right? 5/16 16ths n squared. Right? Okay, so now we have a very big number. It's 256 is the common denominator. So therefore, how many of these are how many 256s? It's going to be 16 of them, right? So this is going to be 16 plus how many of this makes 256? 4 plus 4 plus 4 plus 1. It's not too bad. So what we have here, 16 plus 4 is 20, 24, 25. So what we have is 25 over 256 n squared. And now we try to see the pattern. And there is the pattern right here. The pattern is if you take 5 over 16 you square it, you get 25 over 256. So it looks like the pattern is going to be basically n squared, and then we're going to get 5/16 n squared, and then we're going to get 5/16 squared n squared. So in general, as we sum the actual work being done in each level, we have the sum as I goes from 0, and again I'm going to say h, some height h, and where's h? I don't know, somewhere. I'm going to multiply 5/16 to the I times n squared. And again, just like before, and you'll see the difference between this one and another one. Just like before, what we can do is we can take this n squared out because it's just not moving anywhere, it's just being multiplied by every term. So it's going to be n squared times the sum as I goes from 0 to h, 5/16 to the I. Now, if you look at this summation can be expanded into its terms. And if we do that, then we're going to have n squared times 1 is the first term, plus, it's going to be 5/16, right? 5 over 16, plus 5 over 16 squared, plus 5 over 16 cubed, etc., 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 until, I guess, we reach the value of h. So we'll say 5 over 16 to the power of h. And again, what is h? Some arbitrary depth. So, we don't know exactly what h is, but we can try to let go to infinity. Because we recognize the fact that this is in fact a geometric series. It's a geometric series where the first term a is equal to 1, the ratio r is equal to 5/16, and n, the number of terms, is equal to h. Right? H plus 1.
Yeah.
H plus 1. So the number of terms equal to h plus 1. So let's find out what that sum is going to be. So the sum, this entire thing, is going to equal to the geometric sequence of 1 minus 1 times 5/16 to the power of h plus 1 over 1 minus the ratio. 1 minus the ratio is what? 11 over 16. So it's going to be 11 over 16. Now, you understand 5/16 is a fraction. It's about a quarter. It's a little bit more than a quarter. It's 1/16 more than a quarter. As we keep multiplying 5/16 by 5/16 by 5/16, by the time we get to about 10 times, this number is getting really, really small. And it's approaching 0. So, in fact, if we take the limit as h plus 1 approaches infinity, which is the same thing as h approaches infinity, because if h approaches infinity, then h plus 1 is also approaching infinity, then this piece right here will go to 0. And therefore, our limit will simply be equal to 16 over 11. 16 over 11, which is, I guess, approximately maybe 1.5 or so. Let's call 1.5. Now let's see what the heck that really means. Is that just mathematical mumbo jumbo, or does that really have some meaning? Well, what does that 1.5 represent? That 1.5 represents the case where the number of levels in the tree is infinite. It means that we don't even care how many you have, we'll let them go to their absolute maximum. More than there possibly could be. But even so, if we sum the amount of work being done, that sum will converge to a finite number, 1.5 times n squared. So therefore, our result here ends up being, this whole thing here, the summation here, ends up being about 1.5 n squared. So what does that mean? What does that tell us? Does that give, so remember, this is a function. I know that it cannot be any less than n squared because level 0 is n squared, so I know that's a given. But I also said that this tree expands infinitely with the same progression of work, actual work at every level, that will sum to 1.5 n squared. So I want to know whether we have achieved some knowledge about the complexity of this algorithm, even though it's not suitable for the master theorem. Could this algorithm have a complexity less than n squared? No, we already established that. It cannot be less than n squared. So it's n squared or less. Done. Now here, we expanded this tree ridiculously to infinity using the pattern of work as it's being generated. And even if we expand this tree to infinity, it's still, so beyond what the actual, so this is more than the actual work is going to be. You understand what I'm saying? Because we're saying that every level is going to keep going. But we know some of the branches are going to drop out. We know it's going to look kind of like this. There are going to be dropouts. We're saying it's just going all the time. So, we know the complexity cannot be less than n squared. And we know that when we overestimate it, its upper bound is theta